In this question, you're being asked to rank the basicity of the following compounds in order of the weakest to strongest base. So there's a couple ways we can do this. One way involves a little bit more memorization when you're just memorizing pKa values, because remember, the stronger the acid is, the lower the pKa value is. The stronger the acid is, the weaker its conjugate base is. So we'll go that route first. It's not my preferred method because it involves memorization, but it is helpful. All right, so what we'll do is instead of looking at these bases here, let's look at the conjugate acids. So meaning let's put the proton back on each of these species so we can actually look at the acid species it came from. Okay, so I'm just putting a proton back on each of these. Okay, all right, well, we have an alcohol on the left, we have an alkene, we have a carboxylic acid, and we have an alkyne. Let's put down the pK for each of those. And this is where the memorization comes in. So your typical alcohol has a pKa of about 18. Your typical alkene has a pK of about 42. Your typical carboxylic acid has a pK of about 5, and your typical alkyne around 24 or so. All right? Now remember, stronger an acid, the lower the pKa. The stronger the acid, the weaker its base, the more stable the base. That's why it was a more acidic acid to begin with. All right? So what we can do here is we can just start ranking these. Well, we know the carboxylic acid with a pK of 5 is the most acidic, so it must have the most stable base. The next acid, pK of 18, that would be the next acidic. So it means it has a conjugate base less stable than the carboxylic acid's conjugate base. All right, and then the next one, pK of 24 for the alkyne, and then the alkene, pKa of 42. So what this means is the conjugate base of the carboxylic acid is the most stable base. So it's the weakest. The conjugate base of the rest, let me draw these out here. Get rid of the proton because I'm drawing a conjugate base now. So negative charge on oxygen, negative charge on this carbon, and negative charge on this carbon. All right, so now we know the conjugate base of the carboxylic acid is the weakest, then the conjugate base of the alcohol, then the conjugate base of the alkyne, and then the conjugate base of the alkene. So here we have the weakest, and here we have the strongest. Okay, that's the memorization way of doing this. It's not my preferred method. What I would rather you do is look at the conjugate bases that we already had up here. So I'm going to move the acids down here. Get them out of my way. Don't even want to look at those anymore. All right. Well, we already know this one on the far left, it must be the weakest, and then this one, and then this one, and then this one. But let's figure out why that is. And this is the preferred method because this doesn't really involve any memorization. It just really involves you evaluating the stability of each of these bases. All right, so what do bases do? We're going to use bases to reach out and use their electrons to grab some sort of proton. Well, the less stable, the more unstable this base is, the more willing it is to grab a proton. You can also think of it as how available are these electrons. If these electrons are not very available, they're not going to go out and grab a proton. But if they're really available, they're going to go out and grab that proton. Okay. All right. Well, let's look at all these species. So in these two, we have negative charge on the oxygen, and in these two, we have negative charge on the carbons. All right, well, the first thing we want to know is, where's the negative charge more stable, on oxygen or carbon? Oxygen's more electronegative than carbon, which is why these two species are weaker bases. They're handling that negative charge better than the negative charge on carbon. All right, well, now let's evaluate why is the carboxylic acid conjugate base, why is that one weaker? Why is this one the weakest base? All right, and that's because it's the most stable. And why is it the most stable? Because it's handling the negative charge the best. What makes it handle negative charge better? The negative charge is on oxygen in both of those. But in the one on the left, that negative charge is delocalized. It can be moved around. And if it's being delocalized, it's being stabilized. And therefore, it's less reactive as a base. All right? So that one is the weakest base because those electrons are delocalized. Again, I said you can think about it as how available are those electrons to pick up a proton? Well, if they're moving around, they're less available. All right? Then the next one is the oxygen with negative charge that can't move anywhere, this methoxide ion. It's just stuck there, but oxygen handles the negative charge better than carbon, which is why these ones come next. All right. Well, between these two species, the negative charges on carbon in both of them. There's no resonance in either of these. Okay. So what makes one carbon handle the negative charge better than the other? Here's the difference between the two. In this one here, that carbon is sp hybridized. And in this one here, that carbon is sp2 hybridized. So that's the difference. All right. Well, clearly, since we already put this one here, we're saying this one's more stable. It's a weaker base. Okay. Why is it handling the negative charge better? All right. Think about what an s orbital is. An s orbital surrounds the nucleus. It's closer to the nucleus. What's inside of the nucleus? The protons. What kind of charge do protons have? Positive charge. What is positive charge going to do to the negative charge? These electrons here. Those protons are going to be sort of holding on to those electrons, making them less available to go out and grab a proton. And that's what bases do. So if those protons are being held onto more tightly, they're not as basic. All right? Think of it like this. This is made up of 50% s orbital character. Okay? sp2s are made up of 33% s orbital character. All right? So an sp orbital, an sp carbon, is more electronegative than an sp2. So it handles that negative charge better. It's more stable. Also think of it as those electrons are less available to go grab a base, which is why this is the next one. And then the sp2 is handling that negative charge the worst, which is why that is the next. So that is the strongest base on the far right and has the weakest base on the left. I prefer you be able to evaluate the negative charge and how stable it is to figure out which structure is the most basic. It's much better than memorizing pKa values, although that can help too.